I'd like to now introduce our next speaker, Anat Usatinsky, who will be talking about implantable, battery-free, Bluetooth-enabled, multi-wavelength spectroscopy devices. Please take it away, Anat.
Yeah, thank you for the introduction. All right, let me know if you can see my screen. Perfect. Okay, so my name is Anat Usatinsky, and I'm a part of the University of Toronto Biomedical Engineering Institute. And it is an honor to be presenting to you today about my master's research project at the Franklin Lab. So spectroscopy is an important non-invasive quantitative tool used both in clinical and in research settings. It utilizes components, absorbance, and excitation spectrums to identify their unique signatures, and as such enables us to identify things such as vital biomarkers, which could be used for disease detection, prognosis, and tracking. Now, spectroscopy as we have it today has a few limitations. For example, it needs physical tethers, such as for optic fiber spectroscopy, and when they're using bulky head stages. It also requires anesthetics and special apparatuses, such as when an EPR system is used. And it has the innate limitation due to light penetration depth, which doesn't allow it to penetrate substances deep, and such can't reach deep vessels and deep tissues. For example, with near-infrared spectroscopy. That limits our ability at investigating deep tissue hemodynamics. It could be used for oxygenation studies, perfusion, and circulation. There have been previous attempts at making invasive spectroscopy, such as attaching them to endoscope heads and creating semi-implantable devices. However, none were capable of what our device is capable of, which is utilizing radio frequency power harvesting, utilizes low energy Bluetooth microcontrollers, and is very modular. By creating an implant that is capable of being implanted under the skin, we're able to reach those deeper vessels and deeper tissues. And what we used for our device is called the Texas Instrument Max 3101, and we also use a 3102 chip. And the 3101 chip is capable of red, infrared, and green transmission and reading. So to create our devices, we had a few aims. We needed to make an appropriate design and manufacture the optical implants. We needed to test our device. We first started with creating a device that is capable of just red and NIR transmission and absorbance. And then we created a red, NIR, and green capable device. Our workflow was we needed to design a device that is small, flexible, and function focused. As such, we included suture flaps, and we also encapsulated them in an animal focused method. We then tested the current consumption that is needed by the device, encapsulated them, and implanted them into rats. We also validated our device against standards such as the Finoprestova, and we saw that in the same amount of time frame, and I could see here that the timestamps are slightly incorrect, we get around the same amount of peaks, which suggests to us that this is a valid approach to detecting heart rate. So after we designed and manufactured our wireless optical device, it was time to validate our device using marine model studies. We essentially created a protocol for an 8-week study in which the device would be implanted, and then we would test the functionality of the device once a week by coming in and putting the rats into the radio frequency setup that we built. And then we added an optional hypoxia study. And at the 8-week mark, we performed histology analysis. For the animal focus encapsulation, we first coated the device with a 12 micrometer layer of terylene, which is impermeable, which means no water can get in or out. And we also coated the device with PDMS, and we created various molds, and we chose the mold that we saw was best fit, and we consulted a vet. When we came in for a functionality test, this is just one data set of an animal as it's waking up from isoflurane. we were able to see that we can actually detect both breathing artifacts and heart rate. We were also capable of seeing that our device is able to pick up on small frequency changes, such as here in the breathing rate as the animal wakes up, and in the heart rate as the animal wakes up from isoflurane. In a slightly different perspective, this is a spectrogram, which essentially plots the frequency over time. And we do see the frequency of heartbeat and breathing increases over time. And this is an expected physiological phenomenon that occurs as an animal wakes up from isoflurane. Now that we have created a device that is capable of red and AR transmission and capable of picking up heart rate and breathing rate, we decided to incorporate a green LED. And the reason that we would like to incorporate green LED is because the green wavelength has a shallow penetration. It allows us to probe a different depth of tissue, allows us to potentially do pulse time delay analysis, and it's good for observing blood volume changes. In order to do that, we needed to modify our device. We changed one of our LDOs for a stronger LDO, and we swapped out the 3102 max chip that was used for the red and an AR device to the 3101 that is capable of all three LEDs. And then we followed a similar process as the previous device. Our initial trial, where we used our old radio frequency setup, showed us that we still have a lot of work to do because we had a lot of data dropouts and the device wasn't capable of functioning for more than 5 seconds. So we came up with a few strategies to troubleshoot the green LED. First, we created a more powerful power supply that we're able to tune with our computer. Then we also wanted to look at the impact of actually the PDMS layer on the signal quality. And we saw that when there is no layer covering it, the signal looks like this. And this is just a data dropout, but it is definitely attenuated when there is even a thin 0.5 millimeter layer of PDMS, but that seems to change when we add a black barrier to it. As such, we decided to do the two following things. Number one, we wanted to optimize the PDMS coding, including a barrier. Essentially, we're just trying to push all the light into the tissue and into our photodiode, as opposed to the light scattering as it pleases and potentially doing some backscatter over here. So we wanted to test the barrier width. So we created lots of different segments and widths of PDMS covering the photodiode at various depths. We then also decided to optimize the device coding by looking at various thicknesses, and we created 6 different thicknesses of PDMS, and then we put it on our device. And we also embedded a black barrier into them, and we wanted to see the difference between having just PDMS and a black bare PDMS of those various widths. After we saw our results, we encapsulated our device using a 2-part 3D printed mold. And this is what it looks like. The black barrier could be seen over here. And we were ready to implant into our second animal trial. For this animal trial, we had 4 rats, each one this time having 2 devices, giving us a total of another 2 NIR and red cable devices inside an animal, and 6 NIR red and green capable devices. The goal of this animal study was to see the impact of device placement, top and bottom, see impact due to time to see if the signal is attenuated. We wanted to really test the green LED capabilities. We wanted to include more standards and include an hypoxia event. The standards that we included for both of our setups, for the functionality test setup, we had a PhysioSuit pop oximeter, and for the hypoxia test setup, we actually intubated our rats to keep a breathing rate constant. We had an oxyflow laser Doppler and a mouse stat paw clip oximeter. For our functionality test with our implant, we're able to see that our device is capable of picking up heart rate and breathing rates. And here I included a spectrogram of just the green channel because we saw that the NIR and the red channel are capable of picking those up. And we do see faint lines appearing. And then for our hypoxia study, we put a rat under intubation. We then exposed it to room air and then to 10% CO2. And this is what the signal looks like. It's quite clean. And this is also on a wired device. This is not an implanted device. We just wanted to see if our device is capable of picking up those signals. We also saw using the laser Doppler that we did induce a response from the vessels. And we saw this response being reflected in our spectrograms of the various channels. And we saw that using the our device is capable of picking up those changes of a lowered heart rate throughout all of the channels. We then wanted to create a more complex epoxy event. So we divided this event up into 4 different CO2 and oxygen combinations. And this is what the signal looks like on the wired device. And then we also wanted to compare what we saw to the mouse paw clip. And over here we see oxygen saturation, which drops with every level, heart rate and breathing rate. And when we looked at our spectrogram of our wired device, we did see that we are capable of seeing this similar waveform to what we saw with the heart rate graph of the paw clip. And here I put it on top. So that suggests to us that our devices are capable of picking up more complex epoxy events as well. Now, in terms of our implant spectroscopy from the same trial, we do see that we are capable of picking up some heart rate and some breathing rate. However, as time progresses, the line does seem to disappear a little bit, so we still have a lot of work to do there. I also included a dashed line over here so we can follow the line. And we do see that as the epoxy event starts, the lines do shift up as expected, but there's still a lot of work to be done in order to clean this data up. So overall, we're capable of creating 2 devices that are capable of NIR and red, and then 1 device that is capable of an additional green LED. We were able to create a wireless spectroscopy device that doesn't need for physical tethers, no special apparatuses, and we're able to operate substantial levels beneath the body. In addition, data that I didn't show here, our devices were operable when the animal was moving and alive, awoken from the isoflurane. For the future work, we want to increase the wireless capabilities of our device because we believe that our green data would be much more improved when we have stronger capabilities, and as such, we're thinking of including a battery. We also want to investigate the capabilities of including a green LED and really see it in action. So we want to demonstrate its ability to detect blood volume changes and blood pressure. And one such study that we started doing, this just a preliminary study, is an ice bath study to try changing our blood pressure. And we also want to prolong the lifespan of the device. And this is our next animal trial that we're planning. These are histology analyses taken from our very first animal trial. And we do see that there is a fibrotic capsule forming around the devices, which is not ideal for optical-based devices, and also constricts the device and limits its lifespan. I would like to thank the BCI organizers and participants. Thank you for listening to my talk today. And I want to say a special thank you to the Franklin Research Group at U of T, and I'd be happy to take any questions.
Thank you so much, Anat, for that wonderful talk. I know that we actually have a couple of questions. So we'll start with Eleanor, and Eleanor, please feel free to jump in.
That was a great talk, Anat. Thank you very much. Very exciting data here. So I guess I have a couple of questions for you. One was, obviously, this is only small animal studies right now, but presumably the intent is to use this, obviously, in humans. And how easy is it going to be to have this device that you can insert and remove? That's my first question. And my second question is the intent to use this in hospital, or once you develop wireless to have this for outpatient use? I know big speculations, but maybe you can just jump in and answer those.
Yeah, so this device is a little, it's around the same size of a dime. It's 20 millimeters lengthwise. It's not very large. It's quite compact. I actually had a figure with my finger in it for reference here. So this device is very, very small. So implanting it into a human, what we still have a lot of work to do to get to that stage, is definitely feasible. Now, in terms of the removal, that is definitely a good question that personally right now I'm so focused on just getting it into the human that I'm imagining just that. But from what we saw with the animals, it's quite simple. There is a fibrotic capsule that forms around it, which kind of creates a pocket around the device. So it's quite simple to remove. I included a photo of the pocket in my last slide over here. And then the device comes out clean. It's not attached to anything once the pocket is open. Regarding the, your second question was,
so as an outpatient device, would monitor somebody for, say, I don't know, 2 or 3 weeks?
Yeah, great question. So as I view it, I would like this device to be an outpatient device that is a complementary device to a device such as CardioMEMS, or it could potentially be used to study different organs such as liver and fibrosis formation and calcium accumulation in different organs. So I would view this as an outpatient device. And my whole goal from our research is to create more outpatient devices to kind of alleviate the burden that is on the healthcare with today's increasing healthcare demands.
Thank you.
Thank you so much, Anat. This is really just some wonderful data. I'm sure we're going to continue to have a lot of questions in chat, so please stay tuned for that.